Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. Today we think we've got a great topic for you. It's another one of those topics that came in based on a request by a customer. So today's topic is Micro OCS I/O tricks. So again, we think it's going to be a fun topic today. And joining me again today is Mr. Casey Gardner. How you doing today, Casey?
Hey, not too bad. How's it going, Chuck?
It's going really terrific. Now, the Micro OCS, especially the X4, Micro OCS is our fastest growing OCS family, and the X4 is our fastest growing model in the Micro OCS family, or as an OCS in general. And it's got a lot to offer in terms of the amount of I/O and the amount of capability it has for a really great entry-level price. Now, what are some of the requests that you've gotten from customers in terms of things they'd like to see us add to the I/O family, or to the Micro OCS family, I should say?
Yeah, we've gotten kind of a number of things. I mean, with the Micro OCS, kind of like you mentioned, it's a very complementary feature set and a really competitive price. So there are some things that we did to try to keep it low cost. So things like 0 to 10 volt outputs or something we didn't quite include in the readily available hardware that, but there's also things like graphics where we had a limitation on screen objects of like 30, I think, when we first released, and we were able to up that up to 100 here recently. So we're constantly taking some of that feedback and trying to implement it more and more, or where it is available in the Micro OCS for sure.
You betcha. And today we're going to talk about some of the things you can do in the application from an I/O standpoint that really gets rid of some of the limitations that people are asking about. So we're going to show you some great tips and tricks, and we're going to demonstrate some of those with live demonstrations as well. Okay, so Casey is going to be manning the chat today. So if you're watching this live, go ahead and chat in your question. Casey will get it answered right away, or save it until the end. And then secondly, if you're watching this on replay, then don't hesitate to give us your questions. Just do so in the comment section. Okay, let's get started. Okay, Micro OCS I/O tricks. Let's take a look at our agenda for today. So we're going to do a quick one-slide review of the Micro OCS built-in inputs. And I say inputs because I know the topic or the title says Micro OCS I/O tricks. Today we're really going to focus on the tricks on the inputs, whether you're talking digital inputs or whether you're talking about analog inputs. So after we do a quick one-slide review of the built-in I/O, next we're going to take a look at what are some of the ways in which you can apply digital sensors. We're going to take a quick look at standard PNP and NPN sensors. Those are the ones you're going to run into the most. We're going to take a look at open collector NPN. Sometimes you'll have an oddball type sensor, maybe an encoder or something, that has an open collector or open drain type output, and you want to know how can I apply that along with regular PNP type sensors on a Micro OCS. Then we're also going to talk about AC. What if I have a couple of AC inputs? How can I handle those? Then we're going to switch from digital to analog. We're going to talk about 4 to 20 milliamp based sensors. We're going to switch over to RTDs. We're going to talk about some other styles of analog, 0 to 10 volt, thermocouple, and load cell. And then we're going to talk just for a minute about what about isolation on the analog side? When do you need isolation and how would you add it? All right, let's dive right in. Okay, so this is our quick review of the Micro OCS I/O, at least on the input side. Every Micro OCS unit, from the X2 all the way through the X10, has 12 or 24 volt compatible inputs, and there's 12 of them. They can be used either in positive logic mode or negative logic mode. However, all inputs must be configured the same. So you don't have the choice of configuring them in groups or configuring them one at a time. It's effectively they're all positive logic or they're all negative logic. On the analog side of things, Basically, you have your choice between 4 to 20 milliamp input range or 0 to 20 milliamp input range. Okay, and you've got a resolution of 12 bits. Now, the way the scaling works is the analog inputs are scaled from 0 to 32,000 counts, but they're 12-bit in resolution. So that means that you've got, out of those 32,000 counts, you have about 4,000 unique codes, okay, or unique values as you step up from 0 to 32,000. Now, with the Micro X4, X7, and X10, in addition to your milliamp inputs, you can also use them with RTD PT100 temperature sensors. Now, it's not the full range. The full range on PT100s is, I believe, minus 200 to plus 850 or something like that. The range that we're supporting is from minus 50 to plus 200C, which is the most common range for a whole variety of applications, including things like environmental type applications, building control, even some brewing and those sorts of applications, those sorts of things. And then the resolution on the temperature inputs, or the RTD inputs, is about 1/10 of a degree Fahrenheit. Okay, it's a little better than that actually, 0.05 C. Okay, so that's a quick review on the inputs for the Micro OCS. You've got 12 digital inputs and you've got 4 analog inputs. Let's start on the digital side and let's talk about just standard run-of-the-mill PNP and NPN style sensors. Could be proximity switches, those sorts of things. Okay, now as I mentioned earlier, the Micro OCS is compatible with both. What is the difference? Well, with a PNP type sensor, you're going to connect that up so that it's passing the positive DC signal from the sensor into the input pin of the OCS. And then the common connection is made separately. On an NPN sensor, it's actually the common signal that's being passed from the sensor into the input pin of the OCS. PNP, also called positive logic, is far and away the most popular, and it's what most people use nearly all the time. And I mentioned before, all inputs are configured the same. So if you take a look at an NPN and a PNP sensor, let's start with the PNP sensor in the center there. Okay, you can see that typically if it follows the standard color codes, you're going to have a brown, a black, and a blue wire, where the brown is your positive DC, your blue is your common or 0 volts, and your black is your signal wire. Same thing on the NPN from a color code standpoint. The only difference is, as you can see, with NPN, the load, in this case the OCS digital input, in the case of NPN, the load is between the signal and positive as opposed to between the signal and ground or 0 volts. So those are standard PNP and NPN sensors. Let's talk about a situation that I get asked about fairly frequently, and that is customers that say, hey, I've got PNP sensors for just about everything, but I have this encoder or this other oddball sensor. It's NPN. How can I integrate that? Is there a way I can integrate that while still using PNP for the rest of my sensors? And the answer to that is yes. It's not the easiest thing in the world. It does require an external component that I've drawn here on the screen, but it's certainly possible. Okay? Basically, you're going to use an external pull-up resistor. And in the case of the OCS, you're almost always going to be using an external 10K pull-up resistor. And I'll explain why here in a minute. First of all, in this diagram, you see I've got an open collector type output device drawn in kind of dark gray on the left. And I have the OCS input circuitry drawn on the right. You can see inside that orange box, there is a 10K input resistance that's drawn in, that's internal to the OCS circuitry. And then you also see connected to 24 volts there at the top center, an external 10K pull-up resistor. That is something that the user or application engineer does have to add. Let's talk about how this works. Okay, let's start with the open collector output being off. So remember, the open collector output is acting as a switch. So when the output is off, it is not making a connection between its output pin and 0 volts. Okay, so it's basically open. The output pin is open at that point. So what happens then is that the circuit flows from 24 volts through the 10K pull-up resistor and then through the 10K internal input impedance on the module and then to ground. So that means that the 10K external resistor and the 10K internal resistance effectively are dissipating an equal amount of the 24 volts, basically 12 volts each. That results in having 12 volts across the input pins on the OCS, which results in an on, okay, because everything over 8 volts is going to be an on. So even though the open collector output is off, the OCS will see that as a 1 or an on. Now let's see what happens when we switch that open collector output. So when you switch the open collector output, when that device switches, I should say, okay, now there is a short or a path between the output pin and common, and so therefore you can see, drawn in red, how the signal flows in that case. Okay, so it effectively bypasses the OCS input and goes straight to ground, and effectively that 10K pull-up resistor is going to dissipate the entire 24 volts. Okay, so a couple things we want to check here to make sure that everything's the way we want it. First of all, let's make sure that we don't exceed the maximum current rating for that open collector device. So if we want to calculate the maximum current that we're going to be running through that switch, and you can see there on the screen, it comes out to effectively 2.4 milliamps. So with most open collector outputs, they can handle typically up to 10 milliamps. So we should be good there at 2.4 milliamps. The other thing we want to double check is the wattage on our pull-up resistor, because 2.4 milliamps is the maximum current that's going to be flowing through that resistor when the open collector output is on. And when we do that calculation, we can see that's 0.06 watts, pretty small. That means we can use a 1/4 watt or an 1/8 watt resistor, no problem, as our pull-up resistor. Okay, so that's basically how you would connect an open collector or open drain style sensor to an OCS when you're otherwise have the OCS configured for positive logic. Okay, and that can again be useful if you've got an oddball sensor like an encoder of some sort, for instance. All right, next let's talk about AC, because for the last 20 years or so, 12 and 24 volt type inputs and voltage levels in general have dominated machine control applications, and for a variety of reasons, both of them good. Safety reasons as well as ease of certification. There's a whole lot less safety testing and other types of testing that have to be done at low voltages as opposed to higher voltages. So that's even more reason to switch over to DC. But when you do have AC inputs, you're most often going to find those on machine retrofit applications. Maybe a machine that's older and you want to upgrade the controls, but you're trying to minimize how much of the I/O has to be swapped out. Or maybe it's just an application where there are some AC signals that you want to sense. Okay, so there is a good reason to do it from time to time. Now, the Micro OCS does not directly support any kind of AC inputs. However, it does support them through the use or the application of a device called an opto-isolator. And I'm showing there on the screen what an opto-isolator looks like, at least one that's intended for industrial automation type projects. That happens to be one that we sell at Horner. It's a HE-XACD is the part number of that guy. So using an external component mounted on DIN rail, you can convert AC inputs over to DC. Let's take a closer look at that. Okay, so from a wiring standpoint, what you can see there, I've shown the diagram in the bottom center of the slide there. So we start with our AC running through a switch of some sort, and the hot signal effectively is going to get passed into one side of the optoisolator. And of course, there's also a neutral reference that has to be connected as well on the AC side. And then there's optical isolation internal to that device. And then there's a DC side to that device, which you connect to the input of the OCS. Very straightforward. Okay, let's take a closer look at what one of those looks like here. This is one of these optoisolator devices. Here's the AC side. This is where we would connect our AC signal that we want to detect or sense, if you will. This terminal, the A2 terminal, that's where we're going to connect the neutral as the reference for A1. Of course, you have optical isolation here in the center. And then this is our DC side, okay, with the positive output pin here and the common output pin. So I've actually wired this guy up. So there's one right here, okay, and I'm using this circuit breaker here with a manual switch on it to kind of switch an AC signal. So we've got a hot signal running into the top of the circuit breaker, running down the circuit breaker and into the optoisolator. We've got neutral coming into the optoisolator as well. On the other side, we've got our DC connections, and then coming out of our DC connections on the other side of the optoisolator, we have this orange wire here that's wired into a digital input on the Micro OCS. In this case, it happens to be I1. So if we take a quick look at the screen here, you can see we don't have any power happening here, or the voltage is off effectively. So if I turn on the breaker, you can see I get an indication both on the physical device itself, on the optoisolator itself, and then I've also got, of course, the Micro OCS sees that as a 1. Now the beauty of these devices is that you basically use one per AC input that you have. So if you've got, let's say you've got 3 AC inputs total in your system, you would use 3 of these optoisolators, and they're not all that expensive, frankly, and then the rest of your inputs are still available for standard DC type inputs. So that is the optoisolator for AC type signals. All right, let's move along. So we've covered, on the digital side, we've just covered standard PNP and NPN style sensors. We've covered, how can I handle a open collector type situation without changing all of my inputs over to NPN style. And we've also talked about AC inputs. Now let's move over to the analog side of things. We're going to start with 4 to 20 milliamp sensors. Now the reason why Micro OCS has been designed around 4 to 20 milliamp analog inputs is because it's still, after all these years, it's still by far the most common analog signal that's out there. Of course, there's plenty of other types as well, 0 to 10 volts. There are thermocouple and RTD sensors, but 4 to 20 milliamps still dominates in terms of the signal level that's used in industry today. Okay, and so that's why we applied that with the Micro OCS. Now, the Micro OCS is compatible with both self-powered and loop-powered sensors. And we're kind of showing you the difference of, between those on the screen there. So in the bottom of the slide, we're showing you what the schematics, at least externally, what the schematics look like, or the pinout looks like for a self-powered sensor there in the bottom left. Self-powered sensor, I should say. Now, a self-powered sensor has a dedicated pin for you to bring power in. And it has also a dedicated pin for the output. Whereas a loop-powered sensor, that sensor is powered from a loop power supply, and so therefore it doesn't have 3 pins, it only has 2. Okay, so it's got a plus lead and then a output / negative lead. And then when you wire those up, there's the way those are wired is shown on the right-hand side of the slide there, with self-powered at the top and then loop-powered at the bottom. Okay, and I've taken those directly from the data sheet for the Micro OCS. So we think those are pretty straightforward. But again, the Micro OCS supports standard 4 to 20 milliamp sensors And also 0 to 20 milliamp as well. You can select 0 to 20 milliamp on the configuration side as well. Okay, so that's the standard sensors, the most common ones that you would apply with a Micro OCS. Now, that being said, there are other types of sensors that you might want to apply, okay, including temperature sensors. And today, which is much different than it was when my career started, today RTDs have become the most popular sensor today in industrial applications. When I started my career, it was most commonly thermocouple. Thermocouples are still widely used in a lot of applications. However, in the applications where the temperature range works for RTD, a lot of customers have switched to RTD, and that's because they're easier to apply and they're cost effective and they're accurate. Those are the main reasons. Now, as I mentioned earlier in our summary of the Micro OCS capabilities, the X4, X7, and X10 models support RTD PT100 sensors in addition to the 4 to 20 milliamp support. And I'm showing the diagram on the right-hand side there. Now, the range that we support is -50 to +200 C, great for types of applications like building automation or other environmental type temperature ranges, and plenty of other applications as well. Now, you can support, the Micro OCS can support up to 4 RTD channels per system. However, RTD3 and RTD4 share terminals with analog output 1 and analog output 2. So you can't necessarily, if you're going to be using analog output number 1, then RTD3 is not available. If you're going to be using analog output number 2, RTD number 4 is not available. Just be aware of that. Now, from a scaling standpoint, the Micro OCS scales the RTD inputs directly into temperature, and it's in 20th of a degree Celsius type increments. So that means if you want to scale the RTD and display it on the screen or use it in your application, for degrees Celsius, you just divide by 20, take the analog input value, divide it by 20. For degrees Fahrenheit, you can either do the normal Celsius to Fahrenheit conversion, or you can just do the longer equation where you go straight from the analog input right to degrees Fahrenheit. So those are the analog sensors PT100. Okay, let's take a quick look at how those would be applied as well. Let's start with, we'll go back here to our bench setup here. Now, I'm just simulating an RTD here with a resistor. I've got a 150 ohm resistor. 150 ohms is right in the range between -50 and +200 C. Okay, so I've got that connected with some leads, one lead on one side and then 2 leads on the other side, like a three lead RTD. And then those are wired directly into, I think it's one of the analog inputs of the Micro OCS. But really, the wiring isn't all that complicated. Really what it's mostly about, frankly, is about the scaling. How do we take our wiring here and convert that to degrees C and degrees F? Okay, so I'm going to go ahead and switch over to Cscape and kind of show you some simple logic on how we do that. Okay, so in this case, I'm actually, get my mouse here, there we go. This is the first rung is where I'm doing my scaling for my RTD. Okay, so the first thing I'm doing is I'm taking the analog input value, which happens to be mapped down here, coming in from the second analog input into a variable called RTD raw integer. I'm taking that variable, again, directly mapped to the second analog input. I'm then converting it over to a real variable with a similar name, but with real at the end. Then I'm doing my divide by 20, taking, again, the value from the analog input register now in real format, dividing it by 20, and that gives me my value in degrees C, which you can see is displayed on the screen here. Now, to get it to degrees Fahrenheit, What I did is I just went ahead and did a degrees C to degrees F conversion here using a math expression block. Okay, so that's one way of doing RTD temperature scaling in the OCS. There are a variety of ways to do it. This is, I would say, one of the easier ways. Convert from integer to real, do a division, or in the case of Fahrenheit, you have to do a little bit more of a complex math equation, but still nothing too difficult. Okay, let's head back and let's take a look at other types of sensors. Because obviously, as popular as RTDs are, they're not the only sensors that are used that are outside of the 4 to 20 milliamp realm. So generally for other types of signals, whether you're talking about 0 to 10 volts or thermocouples or load cells, or even if you're talking RTDs beyond 200 degrees Celsius. Let's say you've got an application for RTDs, but you're going to be measuring several hundreds of degrees C. In that case, you can't use the built-in RTD support in a micro OCS. You would need to use an external transmitter, just like you need for 0 to 10 volts, thermocouples, and load cells. Now, the beauty of it is that transmitters these days are available in a whole variety of different shapes and sizes and different price ranges. And I'm just showing a selection on the screen there from one of our partner companies, a company out of Brazil called Novus. They make terrific products, temperature transmitters being one of the things that they make, and they make them in a whole bunch of different sizes. You can get them that are DIN rail mounted. You can get thermocouple and RTD transmitters that mount right inside the thermo well. If you're using a thermo well as part of your machine assembly, they have tiny little cable mount type transmitters that just are right in line with the cabling between the sensor and the OCS. And then they also have probes that include the transmitter right inside the probe. So you've got an RTD probe on one end, and then coming out of the handle, the cabling coming out of the handle is 4 to 20 milliamps instead of RTD. So they've got a really nice selection, but that's just one company, a company that we like and a company that we've worked with for many years. But you can get transmitters from a whole bunch of different companies, and they're, again, available in a wide variety of shapes and sizes. And really, anything outside of 4 to 20 milliamps or anything outside of RTD from -50 to +200C, you pretty much need to use a transmitter for that conversion. One of the products I really like that I want to talk about, and Novus isn't the only company that makes these, but that is, I really like programmable transmitters. So it's a single transmitter that can be configured over USB from a PC that allows you to select a variety of different sensors, from thermocouples to RTDs to 0 to 10 volts, etc., millivolts even. You know, for load cells, those use a millivolt output. And it not only allows you to select the sensor you're using, but it also allows you to narrow down the range for that sensor strictly down to the range that you're using. So maybe you're using a RTD up to, let's say, 500 degrees Celsius. You're not using it all the way to +850. It's beyond the 200 that's supported by the micro directly, which means you need an external transmitter. So you would select RTD PT100 from the configuration utility. But since you're only using it up to about 500 degrees C, you can narrow down the range of the conversion to optimize the resolution in your application. So it allows you to get every bit of resolution out of your system that you can. Okay, so it's a really nice solution. And again, multiple companies make these. Novus just happens to be one that we know and that we like a lot. Okay, so that's a DIN rail mount programmable transmitter. Okay, let me show you that transmitter in action. What I have here, this is that universal transmitter. All right, and I'm using a simulator device to simulate a 0 to 10 volt signal. Right now it's showing about 6 volts. Let me go back and show the transmitter screen here. So what's happening from a signal path standpoint is I've got a 0 to 10 volt signal flowing from my sensor, which I'm simulating, into the transmitter, and then a 4 to 20 milliamp signal running from the transmitter into one of the analog inputs of the OCS. And I've got the signal path kind of defined up there at the top. We're going from 0 to 10 volts on the sensor, 4 to 20 milliamps on the transmitter. The OCS's analog input, the A to D conversion happens, and that scales from 0 to 32,000 counts. And then we use logic to do some scaling into engineering units. And in this case, I'm showing both raw number of counts as well as engineering units. And my engineering units that I'm simulating is 0 to 30 PSIG. So as I crank up the input signal here, my pressure reading increases up to the maximum. Let's take a quick look in Seascape at what that looks like from a scaling standpoint. Very similar to the RTD, but not exactly. Okay, so in my second rung here, that's where I'm doing the scaling for this particular transmitter connection. Okay, so effectively, again, I start with the straight analog input. In this case, I've got a variable that's mapped to AI1. I'm converting that to a real variable. And then I'm scaling 0 to 32,000 coming in to 0 to 30 going out in real. Okay, and that gives me my PSIG on the output side. Pretty straightforward. Now, you'll notice there's no extra step there. Even though with hardware, we took an extra step to go from voltage to current, in logic, the only thing the OCS sees is that analog input coming in as 0 to 32,000 counts, and then we can just scale it from there. So that wraps up the universal transmitter. Next, let's talk a little bit about isolation, because that's a question I get quite a bit as well. Now, the Micro OCS analog I/O is all non-isolated, and that's for fairly obvious reasons. That's because of cost limitations. Isolated analog I/O is quite a bit more expensive. It's a lot more expensive and takes up a lot more space physically than non-isolated I/O. And there's only certain situations when you actually need isolation. Okay, so what would a couple of those situations be? Well, one situation in which you might need isolation is, let's say that you've got an application where there's the potential that high voltage could be applied to the analog signal path on a failure of some sort. Let me give you an example. Let's say we're using thermocouples, and the thermocouples are connected using a thermal well into a machine, and that thermocouple sensor is what's called grounded. In other words, the sensor tip itself is physically touching the machine, let's say the ground of the machine, and let's say what that machine is doing is actually using an electrical heater or something to actually do a heating application. And let's say that when that heater fails, that you could have a short to ground that in theory could cause high voltage on that thermocouple, which could make its way back into the instrumentation system. Okay, so that's a situation where if you are concerned about that, where you could consider using galvanic isolation between the sensor and the instrumentation. And when I say instrumentation, I'm talking about your PLC or your Horner OCS, for instance. Another situation where you might need isolation is if you have ground loop issues. Is there potential differences, voltage potential differences between where your sensors are installed and where your instrumentation is installed? If that's the case, again, you might consider adding isolation. Well, if I do want to add isolation, maybe just for one signal, one thermocouple or something, how can I do that? Okay, when the Micro OCS analog I/O is not isolated. Well, you can go ahead and add either an isolated transmitter, and the one I just showed you a minute ago in our demo was an isolated transmitter. Or if it's a 4 to 20 milliamp signal, you can use what's called a loop isolator, which doesn't necessarily convert the signal. However, it does isolate the external 4 to 20 milliamp loop from the 4 to 20 milliamp loop that's connected to the PLC or the Horner OCS in this case. And these devices are widely available if you do need them. Okay, so that's just a quick discussion on isolation. When might you need it and how could you add it? All right, next I'm going to bring in Casey, but I'm just going to go ahead and do it. We're going to try and see if we can bring him in with just his voice. So are you there, Casey?
Yep, I'm here.
Okay, he's kind of low, but we'll make that work. So did I miss anything? Is there anything that I should discuss?
Yeah, one question that actually came up was in regards to the analog signals, or in this case the RTD inputs, and they're asking if they can be calibrated. One of the fantastic features of the Micro OCS is actually that it does indeed support field calibration. I think this is found under the system menu under I/O status and calibration.
That's terrific. That's a good point, and we will certainly cover. I think we have covered calibration of the Micro OCS in another video, but that's something we should probably revisit. So if you're watching this on replay, and it's a few days after, at least a few days after this broadcast, we'll get a link on there to show you either a link to the past video that showed the calibration procedure, or if necessary, we'll record a short segment and kind of go through that again. That's a great point. Thanks, Casey. Anything else we should talk about? One thing I just thought of actually is another question that I've gotten from time to time, and that is, can't I just, if the Micro OCS supports 4 to 20 milliamp inputs and 4 to 20 milliamp outputs, can't I just add, a 500 ohm resistor or something like that to the input or the output and convert that current into a voltage? Okay, or vice versa, depending on if you're talking inputs or outputs. And the answer to that is not exactly. Okay, if you were to do that, because of the way that the analog circuitry is designed on the Micro OCS, both on the input side and the output side, your range wouldn't be a full 0 to 10 volts on the input or 0 to 10 volts on the output. It would be more like 2 to 10. Okay, so if 2 to 10 volts input would be something that would work for you, then yes, you could use an external resistor connected in series between your sensor and the analog input of the Micro OCS. You could do that, and it would give you, with just the resistor, it would give you a 2 to 10 volt conversion, but it wouldn't give you a full 0 to 10 volt conversion, so be aware of that. Okay, I think that'll do for our wrap up. A couple reminders. Don't hesitate to subscribe to our channel if you haven't done so already. If you do that and click the bell, you'll be notified every time we bring a new video online or we go live, either one, okay? Another thing I want to mention, and that is next week, we think we've got a really great program for you. We're going to go hands-on with the OCS and a device from a company called Real-Time Automation. It's an Ethernet IP scanner. So for those of you who are looking to control Ethernet IP type devices from an OCS, this is a device from Real-Time Automation that will allow you to accomplish that. So we think it'll be a real worthwhile program next week. We're hoping to have the folks from Real-Time Automation joining us live for the show. And with any luck, we'll be able to make that work. Okay. Don't forget, we're here every Tuesday at 2 o'clock. And once again, I know we're getting towards the end of this pandemic, at least we hope so. So I just want to mention, please stay safe out there, and we'll see you next week. Take care.